To illustrate the sort of considerations that we have to take into account when performing regression, here we have a very simple data set to be used for a regression task. In this example, we have one input, which is indicated by values along the x-axis, and one output, which are values along the y-axis. And each of these points is a single observation. So you can see that there does appear to be a relationship between the feature x and the label y. In particular, as x increases, it seems as though y also tends to increase, up to a point. Once x gets to around 6, it appears that increasing x further actually has the effect of decreasing y values. So in other words, we can kind of see that there's a trend in the data that looks something like this. So there are several different algorithms that we can apply for performing a regression task. And each of these algorithms will produce a different output, or in other words, a different model. We will study each of these algorithms in detail later in this course, but let's say we want to create a particularly simple model that just fits a straight line to the data. In other words, it assumes that the relationship between x and y is linear. Then perhaps we might get a model something like this. This is a straight line that kind of captures the overall increasing trend in the data. Notice it doesn't, since being a straight line, it doesn't capture the fact that after a point, this increasing trend turns into a decreasing trend. So perhaps this particular model, this linear regression model, might not be sophisticated enough to fully capture the relationship between our feature and our label. Let's say we want to consider a higher degree polynomial, like a second degree polynomial fit. So here we might get a model that looks something like this. This appears to do a lot better in that the curve fits very closely to the data, and it also captures this trend, this feature that once x gets to around 6, the relationship changes from an increasing one to a decreasing one. Let's say we consider even higher degree polynomials. Let's say we fit a 10th degree polynomial to this data set. Then we would get a model that looks something like this. So what you might notice in comparing the quadratic model and the degree 10 model is that the degree 10 model, the curve for the degree 10 model, passes much more closely to each of the data points. If you look at the quadratic model, there are some small errors in the predictions for our training set, for some of our observations. With the degree 10 model, as it turns out, there's actually no error whatsoever. That curve passes through every single data in our training set. So that might lead you to believe that the degree 10 model is a better model since it has overall less error. However, as we'll see later, the degree 10 model has issues in that it doesn't generalize well. It comes up with an extremely complicated rule that performs well on the training set, but it won't necessarily generalize well to new observations. Just as a quick example, let's come back up and look at the original data. Let's say I have an input that is slightly less than 8. Going up to look at the points around with x values around 8, I get these 2 points. So if my x value is right here, I would, just looking at the data, I would probably reasonably predict that my y value would be somewhere around 13. And looking at the quadratic model, you see that if I plug in a value slightly less than 8, go up to the curve, and then go over, I do predict something around 13 or maybe 14. However, if you look at the degree 10 model, if I pick something slightly less than 8 and move up, I don't actually even know what I'm going to predict because it's off the charts. It's maybe something like 25 or so. So you can see that this model is overly complex and probably will not generalize well. That is a phenomenon referred to as overfitting, and we will discuss that in more detail later on. We can also create what's called a piecewise linear model. So this is a modification of the linear regression model where we are still producing kind of a linear model, but we can use different slopes at different places. So here, basically, we can change the slope from being a positive one to a negative one around 6. This also seems to do reasonably well and captures the trend in our data pretty well. There are other models that we'll talk about in more detail later, such as k nearest neighbors or decision tree models. A k nearest neighbor model fit to this data might produce something a little like this. So the curve is a little more complicated maybe to describe than maybe the quadratic model or the linear regression model, but it seems to do a pretty good job of fitting to our data.